So in this tutorial, we're going to pick up on this discussion with temperature, look at a very important application, namely linear and volumetric expansion. And then we're going to introduce two terms that are often interchanged and confused with temperature, namely heat and internal energy, and establish what they mean before we move forward with thermodynamics, calorimetry, and related phenomena. So if we go back to the lesson when we introduced temperature, we said that the temperature of a material can affect its properties, whether it be electrical resistance, the color of the radiation it gives off, or its dimensions. And there are other factors that are definitely affected by temperature. So we're going to look at linear and volumetric expansion when you have a temperature change for a particular material. And the way it's modeled is fairly straightforward. And so we'll do two example problems, and then we'll see where it comes up, especially when we talk about climate change, because that's an unexpected result when you have, let's say, a generally increasing temperature of water or even the atmosphere. So generally what happens with dimensions, be it length or volume, is that as the temperature increases, the length or volume increases as well. Okay? The very important and critical exception to this, especially from a biological standpoint, is water, of all things. Water actually reaches water's temperature, as the temperature of water is decreased, its volume goes down and down and down, and therefore its density goes up until you get to 4 degrees Celsius. So water is most dense at 4 degrees Celsius. Many of you have done environmental systems and lake ecology. That's a really important parameter, because anything less than that, what happens is, for some weird reason that the chemists can talk to you about, the volume starts increasing with temperature, and we know that when you have solid ice, or solid water, which is really the coldest temperature that the liquid can be, it floats on water, so it gets less dense. So it's a weird little type of situation. But by and large, more temperature means bigger volume. Okay, so the equations for linear expansion and volumetric expansion are very similar to one another. So we generally solve for the change in the length or the change in the volume. We can sometimes solve for percent change, which would be a ratio. And so first and foremost, that change in length depends on how much length you're starting with. And that may be a little bit unexpected. So if I have a longer, let's say, steel rod, I'm going to get a bigger change for a given temperature change than a shorter one. But percentage-wise, it will always be the same. That's going to equal the length multiplied by a factor called alpha. That's the coefficient of linear expansion. And then the part that we're interested in here, why this occurs at all, is because there's a temperature. But it's not just temperature, it's because there's a difference in temperature between where it started and what the, let's say, ambient part is. So the bigger the temperature gradient, the greater the change is going to be. And on the volumetric side, it's very similar. Instead of alpha, we have a beta, again, for the volumetric coefficient, and then difference in temperature. So pretty straightforward. Neither in your reference tables, but you should be aware of them. Okay, so let's take a concrete highways built with slabs that are 12 meter long. Let's assume they were constructed at room temperature. How wide should the expansion cracks, understanding this is expand and contract, between the slabs to prevent buckling if the range of temperatures is expected for that particular climate between -30 and 50 degrees Celsius, and you're given the coefficient of expansion for concrete. All right, so it's a pretty straightforward equation. So let's just make sure we know what we're solving for. So how wide should the cracks be? So that's our not quite your uncertainty in length, but how much we should be able to give in that, how much give there is. So that's delta L. So that's going to equal L times alpha delta T. L is given as 12 meters. Alpha is 12 times 10 to the -6. So notice it's a very small value per degree Celsius. And then our temperature range, which is expected for this, is from -30 to 50. So that's going to be 80 degrees. Okay. So multiply those out. I'll do that for you. And we get 0.011 meters. So it's not a whole lot. All right. But it's enough that you got to take into account for. So when you lay the concrete down, between them you put a little rubber type material. 1.1 centimeters is not tiny. And if you don't account for that, then that's going to lead to greater wear and tear on the concrete over the course of time. And I'm sure many of you have noticed that in asphalt and other sidewalks, etc. The expansion cracks or structures that are built in to allow for that. All right, so on the volumetric side, let's take a slightly different problem. So we have a steel gas tank, and because it's steel, it has a certain coefficient of volumetric expansion. And it's filled to the top with gasoline, and gasoline also has a coefficient of volumetric expression. And we want to know, let's say the car sits in the sun, and the car and the tank and the gasoline all warm up together, and they eventually reach a very, very hot temperature of 40 degrees Celsius. The question is, will the gasoline spill out of the tank? Okay, and it might not be obvious why we'd ask that question, but it all boils down to, will the gasoline expand more than the tank? That's not too hard to answer given the volumetric expansions, the coefficients. We don't have to use the full equation, delta V equals V beta over delta T, but what we're really doing is we want to compare these, and how these change for the tank versus the gasoline itself depends on these parameters. Well, this parameter is going to stay the same, the initial volume. The temperature difference for the two is going to be the same, so it's really just a comparison of the betas, okay? So we see that the beta for gasoline is significantly greater than the beta for the steel itself, the tank. So delta V for the gas is greater than delta V for the steel. And you have an issue there. Now, cars aren't designed to let the gasoline spill out easily, but you can see how that might put undue pressure on it and create other issues. Okay, so to finish up, we now want to turn our attention to three similar terms that are often interchanged and make sure we now at this point distinguish amongst them. This is really, really important in terms of vocabulary. So temperature, which we've already discussed at length, so I'm not going to reiterate what that is. Heat, which we all talk about in everyday usage. And then internal energy, a term that we don't use so often, but we now need to introduce to distinguish amongst these. Okay? So we can maybe start off with a situation. Imagine two objects that are of two different temperatures placed in contact with one another. So I can try to illustrate this. Here's one object. We'll call it H for hot, and we put it in contact with something that's, let's say, C for cold. Okay? Or you can think of an ice cube and a room temperature block. Right? Place an ice cube on a table or whatever. What is going to happen to the temperatures of each object? Okay? When they're in contact, and they don't have to be in contact, but that's the easiest thing to visualize. Well, I think most people understand that the hot object will cool, and the cool object warms. Right? Until when? Well, I think most of you also understand, until they are at the same temperature. So if I've got a hot cup of coffee and I let it sit out in the classroom all day, eventually it's going to be the same temperature as the ambient temperature, namely the room. Okay? So why does this happen? Well, we can talk about it from a microscopic level, which we will eventually. But the everyday explanation for this is we introduce the term heat. We say heat flowed out of H and into C. And while that we can explain that, there's a problem with that explanation. Okay, heat flowed implies heat is a something. It's a material. Okay, a substance, if you will. It's substantial. It literally flowed from one body to another. And that's what we used to think way back in the day until Charles Boyle did some very clever experiments in the 1700s. Okay, so what exactly is heat? It's not a something. It's really incorrect to say that heat flowed from one body to another, even though for a lot of situations we can just kind of hand wave and say that's close enough. But for certain situations, we really, really want to be careful of the words we use. So let's try to be a little bit more specific. So first of all, heat is given a symbol, capital Q. Okay, not to be confused with charge. Okay, so if heat is not a something, objects don't possess heat. Objects can have a temperature, okay, but they don't have heat. It is, more than anything, a process, okay, by which internal energy, all right, so that's a new term, is transferred from a hot body to a cold or warmer or a less hot body. Okay, so what's really flowing, if anything's flowing from one body to another, is this thing called internal energy. Heat is the process by which it occurs. And we've learned about another process associated with energy. And so I don't have a dots list, but this is very similar. So think to yourself, what other process changes the amount of energy, but an object doesn't possess in and of itself? Well, that's work. So work is a mechanical process. Heat is a thermodynamic process. And the mechanism or the criteria for which it occurs is this hot to cold. And we'll explain that more later. But that's a very, very, very important criteria. Without a temperature difference, there is no transfer of internal energy via heat flow. Okay, even here I'm using the word heat flow, but we'll stick with it. And when does this quote-unquote heat flow stop? When bodies reach thermal, we'll use the fancy term now, equilibrium. All right, this is the fancy way of saying they are at the same temperature. And in fact, that leads to a new definition of temperature. So one way of looking at temperature is the property that determines whether a system is in thermal equilibrium with another system. Okay, so if two systems are in thermal equilibrium, we can say they're at the same temperature. How do we know? Because there is no energy flow between them due to a heat conversion. Okay, I'm going to skip this one because there's no context for that right now. And this one, we'll come back to this in class. All right, so the last thing I want to finish up with in the few minutes I have left is what is internal energy? Internal energy is given a symbol U. We talked about it last year in Regents, or even AP1, when we talked about energy loss due to friction. You know, if I have a car with potential energy and it rolls down a hill and it's supposed to have the same amount of kinetic at the bottom as potential at the top, but if we find out it has less, we said it lost it to heat. And then I said, well, a better term is thermal energy. And really what I mean is internal energy. Okay, so we're just going to give it the generic symbol U. So right now we have three symbols: T for temperature, Q for heat, U for internal energy. And we're going to develop equations that have them all in it at the same time, or various other things. So what is internal energy as opposed to heat? Well, it's an actual type of energy, like potential, like kinetic. And by definition, it is the sum of the kinetic and potential energy of the particles, it could be molecules, atoms, etc., that make up a substance. So the internal part is we're taking, if you look at a macroscopic object, like a bowling ball, and think of it as a gazillion different particles, those particles aren't just sitting there doing nothing. They are jiggling around, so they have some kinetic, and they have bonds between them, which is the potential. Okay? So what does it depend on? The amount of potential energy an object may possess, internal energy. Primarily, it depends on the temperature. So a hotter body generally has more internal energy, and it depends on the mass. Okay, and that's that second part that students often overlook. You can have a very cold object, but if you have a huge amount of mass, there's a tremendous amount of internal energy in it. And that's something we'll talk about another time, especially with the oceans. All right, so the last little conceptual problem. So let's say I have a tub of 25 kilograms of water at 20 degrees Celsius, and then I have a bucket of 5 kilograms at 100 degrees Celsius. So the first question is, which has a greater internal energy? Well, the tub has a large mass, the bucket has a small mass, 1/5, and then this is at a certain temperature, 20 degrees, and this is at 100 degrees. In fact, you might be tempted to say that this water is 5 times the temperature of that, which would offset it, but it doesn't work quite like that. Okay, the tub has a much greater internal energy by virtue of its greater mass. For something we'll talk about in class, this 100 degrees is not 5 times the temperature of that. It's not even close to being 5 times the temperature. Like I said, we'll investigate that later. Which has the greater heat? Neither. Objects don't possess heat. If we mix them, what will happen? Then what we'll get is internal energy flow from the hot to the cold. not high